Welcome to our discussion today of buffers and pH. Today we'll be talking about how to calculate the pH of a buffer, also how to determine buffering capacity, as well as designing a buffer to be really efficient at a very specific pH value. All three of those things today. Let's get started. So when you calculate the pH of a buffer, to figure out how to do this, let's consider the reaction below. We have this generic acid, HA, reacting with water to produce H3O and A-. Now this HA can sometimes be confusing. This A just refers to any anion that's acidic. So for example, if we were working with cyanic acid, HCN, the A is just referring to the CN, and it could be anything here. Obviously there's no element A on the periodic table, so this is just any acid. So I'm going to get rid of that real quick. So when we do this, our equilibrium constant, we know that Ka is equal to the concentration of the H3O plus, and it's good to note here that you didn't have to write this H3O plus. This could just be H plus, and you can omit the water here. But in reality, that H plus gloms onto a water molecule, creating what we call the hydronium ion. So I've included it for that reason, although it doesn't change the calculations, because the H3O plus concentration is equal to the H plus concentration. Those two values are the same. All right, then, so the equilibrium constant, Ka, is equal to the H3O plus concentration times the concentration of A-, just like any equilibrium equation, divided by the concentrations of the reactants. Now, this H2O, you can't change the concentration of pure water. It is the same concentration, so it doesn't show up in our equation. And this HA is the only thing left. Remember, we always omit pure liquids as well as solids from our Ka, our equilibrium expressions. So once we have that, we really care here about the pH. And for the pH, all we really want to know about is this concentration of H3O plus. So what I'm going to do is I'm going to solve this Ka equation, this equilibrium expression, for the H3O plus. To do that, I'm going to multiply both sides by HA, and then I'm going to divide by A-. So in the end, I'm going to get something that looks like this. H3O plus is equal to Ka times the concentration of HA, because I multiplied by HA down here, divided by the concentration of A-. Now that's no chemistry there, that's just some algebra, shifting things around. Now I know that the pH is equal to the log of H3O plus, or I should say the negative log of the H3O plus concentration. So I can say here that, so I can take the negative log of both sides. So the log of the H3O plus, or if you're more familiar with just log of H plus, that's totally fine, is equal to, and if I do log to this side, I've got to do log to that side, keep the equation balanced, the negative log of Ka times, concentration of HA divided by the concentration of A-. Maybe I clean that up a little bit, because that's pretty sloppy. Okay? Now using properties of logs, I can do a couple things. I can take this, overall expression, and I can break out this times Ka component of it. And when you do, when you have the log of a product of two things, it's equal to the sum of the two logs. So let me show you what that looks like. So negative log of H3O plus is equal to the negative log of Ka minus the log of HA over A-. Having a tough time writing this HA every time. See if I can get it right this time. Whoops, I get it wrong again. HA over A-. So that's my expression at this point. All I did was break this out, and it's the sum of two logs, and it's negative because the overall everything is negative. This side's negative. All right, so far so good. Now let's start simplifying some stuff. Now I know that the negative log of H3O concentration can be rewritten in two letters. That's called the pH. that is what that is. So this is the pH. And this value has a special name as well. It's called the pKa. So just like the pH is the power of the H plus ion, so it's the log of the H plus, the pKa is the power of the Ka, the log of the Ka. And only it's negative log of both, right? So I can say pH is equal to pKa. And I have a new equation now. I can say that pKa is equal to the negative log of Ka. So just like the pH was negative log of H3O plus or H plus, the pKa is a negative log of Ka. All right? And then this is minus the log of the HA over A minus. Now, one last thing that's done to this equation that's typically done is that this negative sign is turned to positive. And when you change the sign outside of a log, you do that by flipping the ratio in the log. So this can be rewritten as pH is equal to pKa plus the log of A minus over HA. This is the final form of our equation. Now again, it's good to note here that these concentrations are at equilibrium, although we'll see in a minute that equilibrium concentrations are very nearly the same as initial concentrations as long as you're working with weak acids or weak bases. And we know that for buffers, we always work with weak acids or weak bases, so it's going to be a good approximation for us. So let's talk about this equation real quick. We know that a buffer is at its best when the A minus concentration is equal to the HA. So when they are a 1-to-1 ratio of A minus to HA, when they're equal. Well, let's look what that does to the equation. If this is equal top and bottom, then the same number divided by itself is equal to 1. And our equation, oops, I said buffer. Our equation becomes the pH is equal to the pKa plus the log, and if these two are equal, no matter what they are, is equal to, the ratio is equal to 1. And the log of 1 is just 0. So at its best, when the buffer's at its best, and these two things are equal, the pH of the buffer is equal to the pKa. So what that tells you is that if you want a buffer that's operating in its optimal range, you need to adjust the pH of that buffer until it equals the pKa. All right, let's do some practice now. This is a key thing here, and that's only when it's at its best, when A minus is equal to HA. So first of all, let's figure out how to calculate the pH of this solution. So what we start here is nitrous acid. So I'm just going to write this out. So nitrous acid, the OS, right, changes back to, when we're looking for what ion it is, it changes back to an ite. I ate it and it was ick, so you OS ite if you forget how to do that. So 8 goes to ick goes to 8, ite goes to OS goes to ite, usually. So this one we're looking for the nitrite ion, which is NO2 minus 1. So the acid is HNO2, and that's going to be plus H2O. I'm just going to write the equilibrium equation out, and that gives us H3O plus NO2 minus. Now we know at equilibrium that this Ka lies really far to the left here, so very little of it breaks up. So when we start with a 0.85 molar solution, we can assume that we're going to have roughly 0.850 molar at equilibrium because very little of it breaks up. And that's going to make our life a lot easier. Now, if we want to do this really carefully, here's what we do. We put in this for an initial concentration here. We'd put an initial concentration here into an ice table. We'd solve the equilibrium expression, do a bunch of quadratic equation, get a value for x, and then we would know for sure what these concentrations are of these two, of the HNO2 and the NO2 minus. The reality is when we do that, we're going to get almost the exact same answer, 0.85, and not doing it is like way easier. So we're going to assume that our concentration at equilibrium is roughly the same as the initial concentrations. And let me write that down real quick. So because Ka is small, which it will always be for a buffer, because we only use weak acids and weak bases for buffers, Ka is small. The equilibrium concentration of HNO2 and NO2 minus is approximately equal to their starting concentrations. And by making this approximation, we avoid the trouble of having to go through that whole ICE table and the calculation for the change in concentration. All right, so we know we have this equation, this awesome pH equation, that is equal to the pKa plus the log of A minus over HA. So let's go through this and figure out what we know and don't know. So we don't know the pH, which is fine because we're actually looking for the pH. So great, we're not supposed to know it. We don't know the pKa, but we do know the Ka, so we can calculate the pKa. So I'm going to put a question mark there. We don't know that one. We don't know the equilibrium concentration of A minus, although we do know the starting concentration, and we're going to assume that the starting concentration is roughly equal to equilibrium. So here we don't know that one yet, but we can figure it out. And here, this 0.85 molar solution of nitrous acid, okay, that's the starting concentration. It's not at equilibrium, but it should be really close to that. So we're going to just fake it a little bit and go 0.85 molar. Awesome. So now we got to figure out this, and we got to figure out this. Let's do pKa first. It's pretty straightforward. The pKa is equal to the negative log of the Ka, which is equal to the negative log of 4.6 times 10 to the minus 4. Now the value for that when we plug into the calculator, we get 3.34. Now alternately, if you had the best buffering capacity for nitrous acid, it's going to happen at a pH of 3.34 because that's when the pH is equal to the pKa. So that would be a fantastic thing to understand right away. All right, now one more thing. We still have to figure out this A minus concentration. So we're going to take 23.6 grams of, you know what, I'm going to fix that. I really shouldn't have used A minus here because we do know what acid we have. So I'm going to just switch those out real quick. I apologize. And this should be NO2 minus, and this should be HNO2. We have them, so we might as well put them. All right, so 23.6 grams of KNO2. I need to convert this to moles so I can get my concentration from that. And then I come down here and I say, okay, there's 85.11 grams of KNO2, and I got that number from the periodic table. Just add up the molar mass. 1 mole of KNO2, and that equals 0.277 moles. And again, this is trying to find the concentration of NO2 minus. 0.277 moles, and then I just take that 0.277 moles and divide it by the volume, which in this case is 0.1750 liters. And I get a concentration of KNO2 of 1.58 molar of KNO2. Now, because there's one nitrite ion for every KNO2, when they dissolve in water, I'm going to get a 1.58 molar NO2 concentration. Now, if this was calcium nitrite, CaNO2, you have to double this concentration when you broke the NO2 off. So be careful of those little details. All right. So now we have a bunch of stuff. We have this, which we need, which is the concentration of the NO2 minus, and we have the pKa here. So now we need to put all these things together. So pH is equal to the pKa, which is 3.34, plus, I don't know what I just did. Let me erase that real quick. Plus the concentration of, plus the log of the concentration of A minus, which is this one here, NO2 minus, 1.58 molar, and divided by the concentration of HNO2, which is 0.85 molar. All right, and when I simplify this, what I'm going to do is first simplify just this part. So the pH is equal to 3.34, and again, that would be the pH if our concentrations were equal, but they're not. And when I do this, it's plus all this log stuff ends up being 0.27. Now this part's interesting. So this part of the equation gives you the pH when at optimum conditions, when they're both equal concentrations. This gives you the change in pH due to the fact that they're not totally balanced. So this is going to be 0.27 higher of a pH than what it would be if they were balanced, equal concentrations. And that makes sense because we added in a bunch of a bunch of NO2 minus, which is this one is the conjugate base, this one's the acid. So if we add in extra concentration of conjugate base, it's going to tend to drive the reaction this way, reducing the H plus concentration, the H3O concentration, and making it less acidic. And sure enough, when we add this together, we get a pH of 3.61, which is less acidic than if it would have been a perfect balance. All right, awesome. That's how you find the pH in a buffered solution. Again, we made the approximation that because it's a weak acid, that the equilibrium concentrations are roughly equal to the starting concentrations. If you want to do this super carefully, you'd create an ice table, you'd calculate the actual concentrations, and you'd probably find it was like 0.849 of nitrous acid, or actually be a little higher, so probably 8.855. And it would make a very small difference in the pH. All right, awesome. Now, buffering capacity. We already talked about that a buffer is has the biggest capacity, or it has the biggest capacity for absorbing H plus or OH minus ions when it has a 1-to-1 ratio. And that happens when the pH is equal to the pKa. So if you know the Ka of an acid, or of a weak acid, you calculate the pKa, and then you want to get a pH that's equivalent to that, and that will give you, where it's going to be its best buffering at that pH. Okay. Now, the amount of acid or base that it can absorb is whether or not the ratio is a 1-to-1. That's going to be its best location, as well as the overall amount of it. You can imagine if you just put a tiny concentration of weak acid and an equal tiny concentration of weak conjugate base, that you're going to end up with not very much extra H plus or absorbing characteristics of the conjugate base. Let me draw that because I don't think that's making too much sense. So if we have this and we have a really tiny concentration of HF to start with, or of the acid, it's going to break a little bit up into a tiny amount of H plus, and then tiny. And if we add some A minus, so they're equal amounts here, you can see that there's very little extra. So this is the acid, and this is the H plus, and this is the A minus. There's very little extra H in there to buffer if you were to add hydroxide, and very little A minus to take away extra H plus. Whereas if you were to make the same thing and you were to get it to where there's a huge amount of HF, you'd also get a bigger H plus and a huge amount of A minus. And that's not actually true. This one should be down here. It should be the same size as the other one. Because as long as we keep the concentration, the ratio the same, so equal concentrations, the H plus will be the same. But now notice all of this extra, because this is the HF, all this extra undissociated H plus that can be used to fix the pH every time hydroxide takes some out. This is the H plus, and this is the, HA. This is the A minus. And look at all this extra conjugate base that if there's ends up being extra H plus added, it can sop it up and turn to HA. So both conditions happen. So the more concentration there is, the more acid or base so not only do you want equal concentrations, but you want large of both so there's more capacity. All right, so for each of these 4 solutions, I want you to rank them from worst to best in terms of their ability to buffer. Go ahead and pause the video. When you think you have your order and you understand why, hit play and we'll talk about them real quick. All right, here we go. So this first one, we have 1.0 mole of nitrous acid and 1.0 mole of sodium nitrite. This would be a fantastic. We have a weak acid and we have its conjugate base, and they're at equal concentrations, so this is a really nice, good buffer. So let's say good buffer. We don't know if it's the best yet. Let's say we find one better, but we know it's going to be a good one. All right, so this next one we have 1 mole of cyanic acid and 1 mole of sodium nitrite. Now notice the conjugate base of this is Cn minus. We don't have any Cn minus here, so we're not adding any buffering capacity by adding this in. So this is having to stand. This doesn't matter at all. This Cn has to stand as a buffer on its own 2 feet. And we know that a weak acid has a little bit of buffering capacity, but not very much. So this is a bad buffer. Right? It might be able to do a pretty good job of counteracting OH minus, some bases, but it's really bad at counteracting acids. All right, so this next one, we have NO2, and the conjugate base of NO2, HNO2, is NO2 minus, right? And we have 3 moles. Ooh, we have 3 moles of KNO2. So that is the conjugate base, so we're going to have a buffer. But notice our ratio is not 1:1. It's a much higher ratio. So this is going to be a mediocre or a medium buffer. It's going to be an okay buffer. I don't know what I'm spelling there. Buffer. Okay. So it's not going to be as good as this one where the ratio is 1:1. Even there's a whole bunch of this, there's not very much of that. All right, this next one. So we end up with 1.5 moles of HNO3. And the one thing to notice here right away is that this is a strong acid. And it won't matter because strong acids do not make good buffers. This is not a buffer. So this one's going to be not a buffer. So from these descriptions, I think we can get them all worked out. So a good buffer would be our best. That would be our number 1 right here. Okay. And this one was a bad buffer, but it was, at least it's a little bit of a buffer. So it's going to be like number 2 is here. And this one was a medium buffer, so that's going to be a 3 right here. This one's going to be a 4 right here. It's not a buffer at all, so it's going to be the worst at buffering. All right, that's our order. Now on these, I want you to calculate the optimum pH that this buffer, that these acids will work as a buffer at. Go ahead and hit pause, and when you're ready to go again, hit play and we'll talk about them. So you remember that when the optimum point of an acid to be a buffer is when its acid, its weak acid, is equal to the conjugate base concentration. And that makes, let me write this down real quick, the pH equal to pKa plus the log of A minus over HA. That makes this whole fraction equal 1 when these two are constant, and this turns to 0 because the log of 1 is 0. So that means at the optimum location, the pH is equal to pKa. So to find the pH that operates the best at, you just have to go to find the pKa real quick, which means that the pKa of this one is equal to the negative log of 1.54 times 10 to the minus 2. Oh, I haven't done these yet. So 1.54 times 10 to the minus 2 log of that is equal to 1.81. So the pH is equal to 1.81 if it's doing its maximum job. So the best pH that this can buffer is a 1.81. If you want a buffer at like 3.7, you could make this into a 3.7 by adding a whole bunch of extra conjugate base, but then it's not going to be a very good buffer at that pH. So you really want to only use this particular acid when you're buffering at or around 1.81. All right, so acetic acid would be 1.76 times 10 to the minus 5. And we take a log of that, and we find that its optimum pH is equal to 4.75. So if you're looking for a buffer of a pH around, with a pH around 4.75, acetic acid would be great to use. If you need a buffer around 2, you wouldn't want to use this acid, you'd want to use sulfurous. All right, now boric, so 7.3 EE to the negative 10, take a log of that, and we get, whoops, sorry about that. We get here that it's going to be pH is equal to 9.1 9.1. So if you need a pH that's basic, 9.1. So when you have equal amounts of boric acid, such a weak base or such a weak acid that when you equalize its conjugate base with its acid, you end up getting a pH in the basic range. And when you have that, 9.1 is its pH. So if you're looking for, I'm misspeaking a lot. So if you're looking for a really good buffer in a pH of 9, you're going to choose boric acid, and you're going to create the concentration of HbO3 equal to the H2BO3 minus ion. All right, that's that one. So let's talk about preparing a buffer. We're going to talk about citric acid. This is the structural formula of citric acid. You notice that it has 3 acidic hydrogens. When we talk about it today, we're only going to talk about the dissociation of one of those 3 acidic ions. And notice that these 3 hydrogens are the acidic ones because they're connected to a carboxyl group. When that H plus breaks off, the negative charge on this oxygen can resonate between these 2 oxygens, sharing that charge and making the H plus less likely to rebond. Whereas this oxygen, if it loses an H plus, that negative charge is isolated on the oxygen, and that's going to make it stick the H plus on really well again and hold tightly. So this is not going to be an acidic hydrogen, and these are going to be more acidic hydrogens. Okay. So you have a solution of 150 mils of 0.25 molar solution of citric acid. Its Ka is right here. So right now we know we can get the pKa pretty easily. How many grams of this would you have to add a buffer of 4.0? All right, so let's look at the equation real quick. So we say HC6O7H7 plus H2O. And one of these hydrogens is going to break off, so we're going to get H3O plus C6O7H7. We lost that lead hydrogen, so this is now a minus. So it's a negative ion. So we know that the pH is equal to the pKa plus the log of this one, the concentration of C6O7H7 minus, divided by the concentration of this one, the acid. So HC6O7H7. Okay. Now let's look at what we know and what we don't know. So we don't know the pKa, but we can find it. I'm going to put a question mark there. We do know the pH, it's 4.0. So that's awesome. That's the pH we're shooting for, right? We do know the solution of citric acid. So we say, hey, we have a 0.25. Now we don't know it at equilibrium, but we're going to assume, because this is so small, that the equilibrium concentration is equal to the starting concentration. So we're going to say this is a 0.25 molar solution. We don't know this one. It's a question mark. And that's okay because we're actually looking for this one. We're looking for the amount we'd have to add. So to find that, we have to first find the concentration. So let's find the things we need. We need the pKa. So up here I'm going to say pKa. That's clearly pH. Let me get rid of that real quick. So the pKa is equal to the negative log of the Ka, which is 7.41 times 10 to the minus 4. And that value is equal to 3.13. All right, so now we've got to start plugging in stuff and get going. So the pH is equal to 4.0 equal to 3.13 plus the log, the log of the concentration of C6H07H7 minus over the concentration of HC6O7H7. Now I'm going to subtract 3.13 from both sides, and I'm going to also then, well, do it in just a second actually. So this on this side becomes 0.87, so that's 4.0 minus 3.13. And that's going to equal to the log of all that mess. I'm going to write it. So C6O7H7 minus over HC6O7H7 concentration. And actually, let's do this. Let's make our lives easier, and we know a number for this, so we can just put in a number. This is going to be 0.25. 0.25 molar. So the only thing we don't know is this concentration. Now to get this next step, we got to undo this log to be able to get this concentration out. So to undo a log, we do 10 to the whatever power. So this is going to be 10 to the 0.87, 10 to the 0.87 power is equal to, and that 10 to the whatever gets rid of the log, the concentration of C6O7H7 minus divided by 0.25 molar. Now I'm going to multiply both sides by 2.25 molar and have my answer. So 0.25 molar times 10 to the 0.87 is equal to the concentration of my acetate ion, or the citrate ion, I should say, O7H7 minus. All right, and when I do this mathematics, I end up with a concentration of 1.85 molar. C6O7H7 minus. Awesome. Now that's not the answer because it's saying how many grams we have to add. So we have our concentration molarity, and we know that molarity is simply equal to the moles divided by liters. So to find moles, we take molarity times liters is equal to the number of moles we have to have. And that's going to equal the 1.85 molar times the 0.1500 liters and I haven't done that one yet, sorry. So that's 1.85 times 0.15 equal to 0.278 moles. So the moles are equal to 2.78 moles of acetate is what we need to be able to get there. And in this sodium acetate that we have here, grams of this, we have one acetate ion for every sodium. So we need to convert this to grams of sodium acetate. So we know we need 2.78 moles of sodium acetate because there's one acetate per sodium acetate. So we need to just convert this to moles. So 1 mole of sodium acetate, I'm going to put an A there to save myself some writing now, is equal to a molar mass of about 214.046 grams. And when I multiply that by the 2.78 moles, I get 595 grams. Now, this illustrates grams of NaC6O7H7. So this illustrates a really important point. To drive the pH, so the normal pH of this solution, the maximum pH of this solution would be 3.13. To drive that pH of 3.13 up to a 4.0 requires an enormous amount of dissolved solid. It seems unlikely that we'd even be able to get 600 grams of this to dissolve in 150 milliliters of water. So when we're looking for a good acid to create a pH, it really needs to be really close to its optimal pH. The farther away you get, the harder it is to achieve that pH. In this case, this may not be an even possible solution to get to because we have to add so much sodium citrate. What we're trying to find here is which of these would be the best suited acid if you needed a buffer with a pH of 3.50. Now remember, if you're going to have a buffer, you want it to be at its strongest possible, highest capacity possible at the pH you're looking for. So go ahead and take your time, figure out which of these you think would be the best acid for a pH of 3.50, and then let's talk. All right, here we go. So to do these guys, we're going to need to figure out their pKa. Now the first thing I notice I'm looking at this is a Kb, and a Kb is not in the Ka family, so we can't find the pKa with the Kb. We need to first convert the Kb into a Ka, and there's this really handy equation that says that Ka times the Kb is equal to Kw. So I can find Ka of this acid if I take the Kw, the equilibrium constant of water, and I divide it by the K sub B. And of course that is equal to 1 times 10 to the minus 14 I should say, sorry, minus 14, divided by 1.78 times 10 to the minus 5, the Kb, and that gives me a value of 5.62 times 10 to the minus 10. Now when I take the negative log of this number, that gives me the Ka. And gives me the pKa. So the pKa is equal to 9.25. And sure enough, just like we thought, this weak base buffers at a basic level. Although that's not always the case, we did run into a very, very, very weak acid who at optimum buffering will actually generate a pH greater than 7 as well. So a basic solution. All right, so this would be a terrible one. It would be really hard to get this 9.25 to drop down to 3.50. You'd have to add tons and tons of the conjugate acid here. So this is the base. The conjugate acid is an H plus this, so it would be an NH4 plus. You'd have to have huge concentrations of this to get the pH down. And when you did that, you would destroy its buffering ability, and you'd probably be hard pressed to get this much NH4 to dissolve. So terrible idea for this guy. This one, we do the pKa, we get a value of, we take the negative log of this number, we get 3.75. So we're like, ooh, that's a pretty good candidate. Although 3.75 to 3.5 is a pretty decent little jump. It might be hard to do. On this one, we'd say we get a pKa equal to 6.37. Wow, that's going to be really hard to lower it down. And to get it from being not very acidic to more acidic, you'd have to add a lot of extra of the acid, H2CO3. You have to add tons of this extra to be able to shift it down. And whenever you do that, remember, it loses its buffering ability the farther away you get from its optimum pH for it. And this last one would give you a pKa equal to 2.12, pKa of 2.12. So the clear winner of this race is this one. So our formic acid, HCOOH, if we needed a pH of 3.5, would be the best one to run a pH, to run that buffer at. All right, awesome, my friends. That's our discussion of buffers. Enjoy your day.